Look around you. What do you see? Your phone, your chair, your coffee mug? These seemingly ordinary objects are in fact extraordinary. They are all composed of matter in its solid form, a state that constitutes the very foundation of our physical world. Solid-state physics aims to unravel the mysteries hidden within these solid structures. It's a journey into the heart of matter, exploring the arrangement of atoms, their interactions, and the fascinating phenomena that emerge. From the transistors that power our computers to the lasers that read our Blu-rays, solid-state physics is the bedrock of countless technologies. But its reach extends far beyond our everyday gadgets. It delves into the fundamental nature of materials, explaining why some are conductors, some are insulators, and some exhibit the bizarre properties of superconductors. By understanding the principles that govern the solid state, we gain a deeper appreciation for the world around us. We can then engineer new materials with unprecedented properties, leading to advancements in energy, computing, and countless other fields. Let's embark on this exciting voyage into the world of solid-state physics. Fasten your seatbelts. It's going to be an enlightening ride. The story of solid-state physics begins with the structure of solids themselves. Let's dive in. Imagine a perfectly organized pattern, repeating infinitely in all directions. This intricate and precise arrangement is what gives crystals their unique and fascinating properties. This is the essence of a crystal, the fundamental building block of many solids. Crystals are not just beautiful to look at, they are essential in various fields, from electronics to jewelry. These repeating units, called crystal lattices, define the arrangement of atoms and underpin the unique properties of materials. The precise arrangement of atoms in these lattices determines how the material behaves and interacts with its environment. Within these lattices, atoms are arranged in a specific repeating pattern called Bravais lattice, named after the French physicist Auguste Bravais. His work laid the foundation for our understanding of crystal structures. These lattices come in various shapes and sizes, each dictating the symmetry and characteristics of the crystal. The diversity in lattice structures leads to a wide range of physical properties, from hardness to optical clarity. Think of it like building with Legos. Different brick arrangements create unique structures. Just as different Lego configurations can build anything from a simple house to a complex spaceship, different atomic arrangements create materials with distinct properties. But how do we actually see these microscopic arrangements? The answer lies in advanced scientific techniques that allow us to peer into the atomic world. This is where Bragg's law comes in. Named after Sir William Henry Bragg and his son, Sir William Lawrence Bragg, this law describes how X-rays diffract off crystal planes, revealing the hidden atomic architecture within. Their pioneering work earned them the Nobel Prize in Physics in 1915. Imagine shining a light through a fence. The pattern of light and shadow on the other side tells you about the spacing and arrangement of the fence slats. This analogy helps us understand how X-ray diffraction works. Similarly, the pattern of diffracted X-rays reveals the atomic arrangement within a crystal. This technique has been crucial in the development of many modern technologies, from semiconductors to pharmaceuticals. Another crucial concept in understanding crystal structures is the Brillouin zone. Named after the French physicist Léon Brillouin, these zones are a way of representing the behavior of electrons within the periodic potential of the crystal lattice. They help us understand electronic properties and band structures. Think of them as energy zones that dictate how electrons move within the solid. These zones are essential for understanding the electrical and thermal properties of materials, influencing everything from conductivity to heat capacity. Crystals may be beautifully organized, but what holds them together? What unseen forces are at play within these intricate structures? The answer lies in the captivating world of interatomic forces, a realm where the invisible becomes the architect of the visible. These forces, often invisible to the naked eye, are the glue that binds atoms together, dictating the mechanical, thermal, and electrical properties of materials. They are the silent engineers of the material world. One of the most ubiquitous forces in nature is the van der Waals interaction, a subtle yet powerful force. Named after the Dutch physicist Johannes Diederik van der Waals, these forces arise from temporary fluctuations in electron distribution within atoms and molecules. These fluctuations create momentary dipoles that attract each other. Imagine two ships passing each other on the open sea. The waves generated by one ship can cause the other to rock gently, even though they are not in direct contact. This analogy helps us understand how van der Waals forces operate. Similarly, van der Waals forces arise from these fleeting fluctuations in electron density, creating a dance of attraction and repulsion at the atomic level. Another important type of bonding is described by the Lennard-Jones potential, named after the British mathematician and physicist John Lennard-Jones. This potential is crucial in understanding molecular interactions. This mathematical model describes the interaction between two neutral atoms or molecules, taking into account both attractive, van der Waals, and repulsive forces. It provides a comprehensive picture of atomic behavior. Then we have ionic crystals held together by the electrostatic attraction between oppositely charged ions. This type of bonding is fundamental in many materials. Think of table salt or sodium chloride. This common substance is a perfect example of ionic bonding. Sodium readily gives up an electron to become a positively charged ion, while chlorine readily accepts an electron to become negatively charged. This electron exchange is the essence of ionic bonding. The electrostatic attraction between these oppositely charged ions forms a strong bond, resulting in a stable crystal structure. This stability is what gives ionic crystals their unique properties. Section 4, electrons on the move, diving into the Drude theory of metals. Now let's talk about metals, those shiny, malleable materials that conduct electricity with ease. Metals are ubiquitous in our daily lives, from the wires in our homes to the circuits in our devices. But what makes them such good conductors? Why do metals excel at carrying electric current compared to other materials? The Drude theory, named after the German physicist Paul Drude, provides a classical explanation for this phenomenon. Drude's work in the early 1900s laid the foundation for our understanding of electrical conduction in metals. Imagine a metal as a sea of free electrons, zipping around like bumper cars in an arcade. These electrons are not bound to any specific atom, allowing them to move freely throughout the metal. These electrons, unbound from individual atoms, are free to move throughout the material. This freedom of movement is what makes metals such efficient conductors of electricity. When an electric field is applied, these electrons flow in a specific direction, creating an electric current. This movement of electrons is what powers our electronic devices and electrical systems. The Drude model also explains the Hall effect, a fascinating phenomenon discovered by the American physicist Edwin Hall in 1879. Imagine a thin strip of metal with a current flowing through it. This setup is crucial for observing the Hall effect in action. If we apply a magnetic field perpendicular to the current, we observe a voltage across the width of the strip. This perpendicular arrangement is key to the Hall effect. This voltage, known as the Hall voltage, arises from the deflection of moving electrons by the magnetic field. The deflection causes a buildup of charge on one side of the strip, creating the Hall voltage. Another important concept in understanding the behavior of electrons in metals is the Fermi-Dirac distribution. This statistical model is essential for predicting electron behavior at different energy levels. This statistical model describes the probability of finding an electron at a given energy level in a system of many electrons. It helps us understand how electrons occupy energy states in metals. Think of it like a game of musical chairs, where the chairs represent energy levels and the electrons are the players. When the music stops, electrons find their places in the available energy levels. The Fermi-Dirac distribution tells us how the electrons are distributed among the available energy levels. This distribution is crucial for understanding the electrical properties of metals and their behavior under different conditions. Section 5. Beyond free electrons, a glimpse into the quantum world of solids. While the Drude theory provides a good starting point for understanding metals, it has limitations. It fails to explain why some materials are better conductors than others, and it doesn't account for the behavior of semiconductors and insulators. To delve deeper, we need to venture into the realm of quantum mechanics. Here, electrons are no longer viewed as simple particles, but as waves, their behavior governed by the enigmatic laws of the quantum world. One such model is the Kronig-Penney model, named after the Dutch physicist Ralph Kronig and the American physicist William Penny. This model considers the periodic potential experienced by electrons due to the repeating crystal lattice. Imagine an electron navigating a series of regularly spaced hills and valleys. The Kronig-Penney model helps us understand how this periodic potential influences the energy levels and motion of electrons in a solid. Another important model is the tight binding model, which considers the overlap of atomic orbitals when atoms are brought close together in a solid. Think of it like overlapping waves in a pond. When atoms bond, their atomic orbitals overlap, leading to the formation of energy bands. These bands determine whether a material is a conductor, semiconductor, or insulator. Section 6. The dance of the phonons. Vibrations that shape the solid state. Imagine a stadium full of cheering fans, their collective movement creating a wave that ripples through the crowd. Similarly, within a solid, atoms are in constant motion, vibrating about their equilibrium positions. These collective vibrations, called phonons, play a crucial role in the thermal and mechanical properties of materials. Phonons are quantized, meaning they can only exist in discrete energy levels, just like the energy levels of electrons in an atom. When a solid is heated, its atoms vibrate with greater amplitude, corresponding to higher energy phonons. This increased phonon activity is what we perceive as an increase in temperature. Phonons also play a crucial role in heat conduction. Imagine heating one end of a metal rod. The increased atomic vibrations at the heated end propagate through the material as phonons, carrying thermal energy along with them. Moreover, phonons interact with electrons, influencing a material's electrical resistance. This interaction is particularly important in superconductors, where the absence of phonon scattering allows electrons to flow with zero resistance.